All right, so we're going to take a look at 2.6, number 12. And the instructions say find an integrating factor that is a function of only one variable and solve the given equation. So, first things first, what does that mean? What am I to do with myself? So, when they're set up like this, you should kind of think to yourself exactness, right? So when you're thinking to yourself exactness, that should be that you're thinking m dx plus n dy is 0. And if I could find a solution that had, or sorry, a function of two variables that had fx was m and fy was n, then my solution would be f of x and y is some constant c. Now, I probably can't do this in this case because they didn't tell me to solve this exact equation. They told me to find an integrating factor and then solve. So what's the difference between having an exact equation and needing an integrating factor?
Their partial derivatives aren't equal.
Say that louder.
Their partial derivatives aren't equal.
Oh, yeah, it's just not exact, right?
Yeah.
So if we check this for exactness, I'm thinking, all right, so I'm going to take this thing and I'm going to calculate m, actually. I'm going to think about that as m. This is n. And I'm going to calculate my and nx. I'm going to have to do these anyways to run that the theorem out of the integrating factors section. So the first thing I'm going to do is calculate these two quantities anyhow. So what's my?
X squared plus 4x plus 2.
Good. And nx looks like 2x plus 1. Oh. Well, those aren't the same.
No, they aren't.
So the conclusion I can draw is that this is not an exact equation right now. So an integrating factor is going to be something that I can take this whole equation, multiply through by, and have it become exact. So how do I come up with such a thing?
Find an integration factor.
Okay. How do I find an integration factor?
Well, two ways. At least that's what the book taught us, is two ways mainly.
Yeah, so I'm hoping that you're looking in the book at this theorem.
Yeah.
Okay, so this theorem says if we have continuous enough partials and we can find a p that's just a function of x or a q like this that's just a function of y, then these will give us integrating factors. So I just need to check if either of those things is true. So first I should just check the continuity. Are m, n, my, and nx continuous?
Yeah.
Yeah, they're polynomials. Check. Right? Okay, then I need to calculate my minus nx over n. So I'm going to take my minus nx and divide by n. And I'm kind of thinking p of x, maybe, is this. So for my, I got x squared.
Really quickly, why do you say maybe if this is supposed to be an exact integrating factor?
Good. I say maybe because I'm not sure whether part A is going to work or part B is going to work, or possibly neither. This theorem doesn't give you all possible integrating factors, but it gives you a possible, like it gives you a spot to look. It does not guarantee that that looking will result in an answer. Right? This is like, I lost my wallet. I'm a look on the couch. I'm a look in the car. Am I guaranteed that my wallet is in the couch or in the car? No. I might find it in the freezer eventually. Right? But this gives me at least a good place to start. And that's really all this theorem does, is give you a spot to start. So first I'm just going to go look for P of X, see if it's in the couch. So I got my my, I'm going to subtract my nx. I'm going to divide this whole thing through by n. And what I'm looking for is this thing a function just of x? Yeah,
Yes.
seems like. I don't see any friggin' y's in there. You guys see any y's in there? Okay, cool. Then I'm done. So I'm no longer wondering, is this P? I'm saying this is P. Right? P is this thing.
The bottom should be x squared plus 1, correct?
The bottom should be n, so x squared plus x.
Oh, got it. Not nx.
Yeah, not the partial, but the actual n. And this is kind of fundamentally the thing that you're most likely to screw up here. I don't expect you to have this theorem memorized. Don't try.
Oh, too late.
Okay, good work.
I wish you told me that before.
Yeah, so in general, if I'm continually copy and pasting something out of the book every time I talk about a topic, it's because I don't expect you to have it memorized.
I just memorized the form before the theorem where it's mu of m minus n x equals the p of x n minus
Yeah.
of ym.
Yeah, that's a better object to have in your memory, I think, than this is.
Yeah.
All right. So at any rate, I just need to simplify this a little bit because I'm going to have to integrate it, right? So I'm going to have an x squared plus 2x plus 1 over x squared plus x.
Mm-hmm.
You guys see anything special about that? Karen?
Yeah, so we can factorize these.
Yep. Top is a x plus 1 squared. And the bottom is an x times an x plus 1. So we can roll up one of those guys off of here. And then splitting across the top, I can see that this is 1 plus 1 over x.
Okay, that, you know what, that right there answers my problem because I don't know why I didn't see that you could factor an x out there, but that was my main issue is I couldn't figure out how to reduce it.
I had a suspicion, but I couldn't quite pin it down exactly.
Yeah, that tends to be the toughest part here is just like, okay, so I found this thing. Now I have to integrate to get my integrating factor. So ultimately here, my integrating factor, mu, is going to be e to the antiderivative of this thing. And if you can't simplify this thing, then you can't antidifferentiate it, and then you're kind of hosed. You can leave it like this if you must, and use the chain rule to differentiate this puppy. It will actually work like this, even if you can't find a closed form, but it'll be really hard to match it against the back of the book. So in this case, I should get a e to the x plus log absolute value of x plus a constant, which simplifies out to e to the x times e to the log of the absolute value of x times e to a constant. So I'm getting that my mu is, let's see, ax e to the x. And then the cool thing here is that you can drop what?
The
A?
Yeah, you can drop the A on these because you're going to multiply both sides of an equation through by this thing, and it's got a 0 on the right-hand side. So if you multiply through by, say, 2x e to the x, well, then you can just divide everything by 2 and get rid of that 2.
Yeah, good point.
Right, so as long as A is not 0, you can multiply through by this. And frankly, if A is 0, probably don't want to multiply your whole differential equation by 0.
Yeah.
Like,
Maybe.
that seems like it's going to be a problem. All right, so all told here, I need to go get my original differential equation. I need to plop it back down. Now, I'm going to take this thing and I'm going to multiply through by x e to the x. I discard that A. So as I go through this, I'm going to have x cubed y e to the x plus 4x squared e to the x. Oops. 4x squared y e to the x plus 2xy e to the x. All that junk dx. And then I'm going to have here plus an x cubed e to the x plus x squared e to the x dy. This is supposed to equal 0. All right. Now, at this point, you have a choice that you can make based on your level of confidence. Are you ready for this?
Second one.
Yeah, I was gonna say, like, why even waste our time with this question? Just go to the second one.
The thing that I was going to say was you could check to make sure this is exact before you go find your function. But to be completely honest here, I'm just going to pretend that I'm confident in myself. I'm going to integrate that second thing, and then I'm just going to check that it was exact by checking that its y partial is the first thing. Pretty good with that? All right, so I'm going to take this guy, and I'm going to integrate d. Which variable are you integrating here?
Y.
Good. We're going to integrate that part dy. And so we're going to get the idea that our function, f of x and y, should be, oh, well, that's really easy. This is just a function of x, right?
And it is exact, by the way.
Yeah, it should be exact. If it wasn't exact, I did the integrating factor wrong, which happens. But okay, so I integrate this y, and then what else do I need here?
Let's see.
Let's see.
Yeah, I need plus some kind of constant or something.
Really quickly, you said if I did the integrating factor right, or then it should be exact. But earlier you said p of x might work when we did it.
Good.
It was only conditional based on whether or not that was a function of just x, right?
Yep. So there are two sources of my skepticism here. The first one was if I calculated p of x and it wasn't just a function of x, then this thing wouldn't work anyways. The second source of skepticism was once I found this, it should work so long as I integrate correctly. And so if I made some kind of flub up in my simplification or my integration, that's on me, right? So if I performed that operation correctly, then this thing is an integrating factor. Because I'm confident that p is only a function of x, there is an integrating factor, but I may have botched finding it. So I'm pretty confident that I found it correctly because that simplification seemed too slick to be happenstance. So now I've got this thing. I got a constant here at the end. What maybe is special about that constant?
Could it be a function of x?
Yeah, that could be a bare function of x, right? Now I should check this when I differentiate it. So if I differentiate with respect to x, I should get this first thing again. You guys see that? So if I differentiate this thing with respect to x, I need a little product rule in here. So I'm going to just calculate fx quick just to make sure I've got all the pieces right. So I'm going to get the first thing here. So I've got an x cubed y times the derivative of the second plus that first thing's derivative times the second. And then here I've got my first thing times the derivative of the second plus the second thing times the derivative, or sorry, yeah, the second thing times the derivative of the first thing. And then I have a k prime of x here. Now I just need to match this. Let's see. So I've got an x cubed y e to the x. Got that one. I got, let's see. I got x squared y's, x squared y's. So all told, I have 4 of those. Oh, yep. I got 4 of those up here. Here I got a 2xy. Here I got a 2xy. All right. So I'm confident on those. And what do I know about k prime?
It's 0.
It's 0. Cool. All right. So this is an honest constant now. So that would tell me that f of x and y is x cubed y e to the x plus x squared y e to the x plus an honest constant. And now what am I going to do with this thing?
Wait, that when you say an honest constant, you mean it's just not a function of x? Because I thought we said it was 0.
The derivative
yes,
of it
k
is 0.
prime is 0, which means that k.
That's right.
So I know it's not a function of x. I also know it's not a function of y. The only thing left in this category is a number. And the good news is that it doesn't particularly matter because the next thing I'm going to do is I'm going to take this thing. I don't know why the blue in here is not quite the same. Is it this blue? It's still not quite the same. So the thing I'm going to do here is I'm going to take my function f of x and y, and I'm going to set this equal to a number, right? So I'm going to say this is some number c. And then k and c are arbitrary constants, so I really only need one of those. What's special about this one? This is actually a cool problem.
You can solve it explicitly, can't you?
Yeah, this one's rad because I can get an explicit solution. I can factor a y out and then divide. So this is going to give me the explicit solution. Y is c over x squared e to the x plus x cubed e to the x. I don't know why I switched the order there. But that's kind of rad. I don't often get explicit solutions here. You guys cool with this? Okay. So that was essentially the process of an integrating factor, right? So our first thing we do is we check to see if it's exact. If it's not, we'll go try to find an integrating factor. We'll multiply through by that, and then we'll just apply the exact technique again. Cool with this?
Yep.
This, by the way, is a technique that will work. You can always use an integrating factor, but finding one is hard. And like I said, this does not give all the possible places your keys could or your wallet could be, right? It just gives a couple spots that are easy to look right at first. Any other questions on these?
Not really. Oh, there is one.
Sure.
If you try to find an integrating factor for an equation that is exact, it looks like the integrating factor is going to be 0.
Yep. Well, okay.
Or
so,
is it just, it comes out to be c? Oh, no, it's e to the 0, which is 1.
Yep.
Okay, yeah, that makes a lot of sense. Okay.
Yeah, so the p you'll get will be 0. And then when you integrate it, you get a constant. And so you're multiplying both sides of this equation through by a constant, which you didn't have to do anyways.
Which is just, yeah, you can divide them both out and get 1. Yeah, cool. All right.
Which is kind of neat, right? This sort of says that, hey, even if you accidentally try to find an integrating factor, it'll still work, which is a reassuring thing for a technique, right? Ethan, did you want to... Oh, sorry, let me stop the recording.